the group table, you can also find the inverse of each element. Okay. So you've got the inverses, and so closure, inverse, and the unit. Well, the unit's obviously this one. So you can generate this unit from these. I don't know, what would that be? Is it just a squared? It gives you a unit? Well, so you can find the unit by just multiplying powers of these and this and this. I'm not, off the top of my head, I don't see what it is, but anyway. All right. Now, these two matrices obey these properties. This to the fourth. Oh, there it is. There's the answer. Here's the answer. So the unit is just this matrix to the fourth. Right? A to the fourth is E. So these elements here of this group obey these conditions, these relations, as they're called. Right? You can show that. Right? Now, given all these properties, you can construct the group table, and you'll find it's this one, which is different from the others, all the others. Right? It's another non-isomorphic group, and it's given the name the quaternion group. And why is that? Because it has properties of the numbers quaternions. Perhaps I could talk briefly. What is a quaternion? Well, it's obviously got something to do with 4 in it, right? Like a 1-minute history of the theory of numbers. The first counting systems were sort of like pebbles. You'd have like one pebble for one sheep. So you're a shepherd, and you'd let the sheep go out of the sheep pen at night to protect them from wolves and so on. So every time a sheep left the pen, you'd put, you'd have 2 baskets, and you'd take one pebble from a supply and put it in your second basket for each sheep that left the pen to graze on the pasture, right? And then at the end of the day, when the sheep came back into the pen, every time a sheep entered the pen, you'd take one pebble out of the second basket, put it back into the first. And if you had some pebbles left over, that means there's some sheep missing. So you'd go out and find them. That's your job as a shepherd, right? The herder of the sheep. Now, that's a pretty primitive sort of numbering system. It's just a 1-to-1. That's a unary system. You only have like one, one pebble. And then people started inventing the integers, the countable numbers, 1, 2, 3, 4, and so on. And then due to trade, people got into debt, and merchants needed numbers that could express the concept of debt. Like this guy, he owes me 3 shekels, so his account with me is -3. And so when he pays me 4 shekels, I make a profit of 1. 4 minus 3 is 1, so the negative numbers. And then people were slicing up pies and so on, so they developed the concept of fractions like 3/4, 3/4. And then Pythagoras' theorem came along, and people noticed that the square root of 2 was not a rational number. It was not of the form an integer over an integer, so hence invented the irrational numbers. And then people were playing around with equations of the form, say x squared plus 1 is 0, and that led to all kinds of weird phenomena. So people invented the complex numbers. They just said, well, we'll just define a number we'll call it I for imaginary, not real, not a real number as people imagined, sorry, people conceived numbers to be prior to complex numbers invention. So they just defined I for imaginary, to be equal to square root of minus 1. All right, and then a whole mathematics came out of that. You get complex analysis, where you're doing calculus, differentiating and integrating on complex numbers. I'll do a whole course on that fairly soon. So the next step was the quaternions. So you had complex numbers of the form x, that's a real number, plus I, square root of minus 1, x plus I, y. So you had one real number, that was the x, and you had one complex number, that was the component, that was the y. And then Hamilton, the famous Irish mathematician, was trying to generalize this concept, asking himself, could you have more complex numbers? Could you have something of the form x plus I, y plus j, z? And he couldn't get it to work. When he was multiplying, and it wouldn't divide, and it just didn't work. And so he had a flash, an epiphany, and he said, oh, well, instead of having like two component imaginary numbers, like y and z, have three. So it's got three imaginary components and one real component, and hence four. And those types of numbers of the following form, a quaternion number is like w, that's the real, plus xi, I is a square root minus 1, plus yj, plus zk. And these I, j's and k's are imaginary numbers. And I squared is minus 1, j squared is minus 1, k squared is minus 1, and so on. And so you get a whole new mathematics, a whole new numbering system called the quaternions. And this group has those kinds of properties. And just for the fun of it, there's also an octonian number system, where you have one real component and 7 imaginary components, and that's all there are if you're going to do division. So these kinds, they're called algebras. These kinds of number systems, or algebras, that's all there are if you're going to be able to divide them. So they're called division algebras. And there's a famous theorem proving, you've classified those kinds of number systems, the division algebras. Like there is no 16 or 32 or whatever. That's it. Eight's the maximum. So it's a famous classification theorem, and I love classification theorems. Proving that the octonions, also called Cayley, C-A-Y-L-E-Y, Cayley numbers, usually just called the octonians. That's it. If you're going to have division of these numbers defined, so hence division algebra. All right. The next session will be on problem solving, and I will do the analysis of G9, G10 and G11. G11 is trivial because it's just a prime number, 11 is a prime number, so that group will just be the cyclic group. So effectively it's just two, G9 and G10. So that will be in the problem solving session.